All right, so may I?
Okay, so after the guest, we are very grateful, first of all, to the BRC that we can be here. Thank you very much.
No, you are very welcome.
And to you especially, because it's, I think, the fifth time you...
Is it?
It is.
Oh.
You only missed the
So
first
many.
one. I think you only missed the first one. That you have been giving us these fascinating talks of the... You have seen Ultrafast spectroscopy, the physical basics of Ultrafast spectroscopy, and now we shall see an application, an intriguing biological application. So thank you very much, and we are looking forward to it.
Thank you, Peter. This is easy for me. I don't have to go anywhere. You came to me, so thank you for that. Right. So I'm Petar. I lead here the laboratory of photosynthetic membranes in the BRC. Now, I don't know, this year mostly medical or mostly physical sciences. Unfortunately, I should disappoint some of you. We don't do much of medicine in our lab. Well, we can grow spirulina if necessary. Some say it's healthy. Mostly we grow spinach though, or pine. We love spinach. That one's definitely healthy. And we love a lot of lasers anyways. So not that we have that many, but what we like, let's say, we study the overall energy translocation and conversion in the photosynthetic membranes. Obviously, that needs a lot of spectroscopic analysis tools. That is one of those that we will talk today, is the two-dimensional electronic spectroscopy. Now, yes, this is an ultrafast spectroscopy, and electronic is just to say that we are using UV visible light to probe electronic excited states. And the key here is the 2D. We have two dimensions. What does that mean? It simply means that instead of one frequency dimension, like in most common spectroscopies, like absorption spectra, we have two frequency dimensions. That's about it. So what does that mean? Now it's the 2D spectroscopy is very strongly related technique to pump probe, transient absorption. Did you have the transient absorption already? Great. So this is just an extension of the transient absorption spectroscopy. So it is like the transient absorption. It's a nonlinear spectroscopy, measures the third order optical response of our system of interest. And like I said, we have two frequency axes, so the two-dimensional spectrum is just a cartoon, is a correlation map between two frequencies that we can call, one we can call excitation, the other some people call detection, some people call emission, or you can call it probe. This would be the pump, this would be the probe. And the thing about this is that this kind of technique basically contains all the information that you can get from many other third order techniques. If you have heard, let's say, pump probe, it's all the information is in there. Transient grating, 3-pulse technique like photon echo, peak shift, or whatever. Everything that you can extract from those is already encoded in the two-dimensional spectra. So they contain a lot of information about our molecular system. Such, let's say, molecular system we represent with these ladders, right? This is just a very simplified Jablonski diagram. We have molecules with excited states, and then these states correspond to some energies, and they will correspond to some peaks in the two-dimensional spectra, and they will tell us information about these states, about their energies, line widths, homogeneous and inhomogeneous, and more importantly, the couplings between the levels, which are here in these cross peaks, and it can tell us about coherencies coherent dynamics, population dynamics or excitation dynamics, pathways, connectivities in the system. A lot of information that we are usually very interested to know what is happening in our systems. Now, well, if you understand everything absolutely, then we pretty much have finished, basically. So, if there are some parts that I am telling and you feel like they're not English, then we can proceed and explain those parts. All right. So we can take it easier at first and introduce some basic concepts, very basic. Sorry guys there, you will have to survive that part. And basic concepts and fundamentals, and that will be the first part, and then we can talk about several implementations, how to build the instruments that will give us such two-dimensional spectra, and finally I will just show you some examples in photosynthesis on light harvesting complexes. Okay, so talking to the very basics. Now we have to treat our system. Let's say we have a molecule of interest, a molecule that is photoexcitable. What does it mean? A photoexcitable molecule means that it has some electronic states which can be triggered by light. We must be able to excite the system. That means to bring an electron from one orbital, if you wish, to another orbital by light, right? So, again, simplified Jablonski diagram means that we have different energy states. These are quantum states of the system that have quantum states of different energies, and each line represents some energy. And we know that these energies and these states will be solutions of the Schrödinger equation, and they will be eigenstates, which means that this will be diagonal. These will be states which come when we diagonalize the Hamiltonian or the energy operator, right? So when we solve what we call the time-independent Schrödinger equation, we get these eigenenergies which corresponds to the energies of the states, and we have the eigenfunctions, here these psi, which are the wave functions, which give us all the information about the electronic information about the system in each of the states. Now, if we have the luxury to calculate fully the wave functions for all the states, then we can also calculate pretty much all the photophysics of the system, including any kind of spectroscopic response or optical response. The most simplest thing that we could be interested is the possibility that we excite the system from one level to another. Let's say this is the lowest level, so that will be the ground state, and the probability to excite it to any other state. And that probability is usually governed by what is called the transition dipole moment, which is simply the displacement of charges between the two energy states, right? So the transition dipole moment is a quantum mechanical operator defined like this. Is just the position of the electrons and the charge, so which is integrated over the two states. Let's say this will be the ground state and this will be the excited state, so it is a change in position of the electrons, right? Okay, so this from Fermi golden rule, remember that this will tell us about the probability that a photon of light interacting with our electron system will cause the transition. More correctly is the probability is proportional to the square modular of the dipole moment, right, which is called the dipole strength. And of course the intensity of the field, and of course the polarization, that means the orientation of the, because this is a vector, right, so the field is also a vector, they need to match in direction in order to induce the transition. Anyways, going further, what happens is that if we have such states that have some non-zero dipole moments, then we have absorption of those states, right? And if we have absorption of certain frequencies of light, so for each state we will have some band and in the absorption spectrum. That is frequency, that is absorption. Absorption is the negative logarithm of the outgoing intensity of light divided by the incoming intensity of light, right? So the height of the peak is proportional to the dipole strength, which is the square of the dipole moment. So it tells us about the change in charges. The position of the peak obviously is what gives us, the position of the peak here is given by omega, which is, as I said, frequency, and more specifically angular, and there is here the key, it's related to the energy, right? It's simply proportional to the energy. Okay, so we know the energy from the absorption spectrum, we know already the energies of the states, and maybe we know the dipole strength. It also depends obviously on the concentration. We don't want to diminish the importance of the Baer law. Also, you notice here I draw lines, but in absorption we never see lines, right? We always see bands. So because we never have infinitely small line width. We have some finite line width, which is governed by various kinds of homogeneous and inhomogeneous broadening effects. Now, let's talk about a bit the homogeneous and inhomogeneous broadening, because that's here. I don't think I have a slide, so let's just put a white screen here. And maybe it's easier if I don't show many slides at all. So let's say, why is the line width? Say we have the same picture. We have an energy level from the ground state, and that's the delta E, or the energy of the transition, and that corresponds to a frequency which can be nu or omega, whatever, on a frequency scale. So if that's a line, that should also be a line. But we always have a band. Why is that? Here?
Because the energy stays as a line width.
Sorry?
Yeah, the energy stays as a line width, so it's not a straight line.
Yeah, okay. Then we have to also draw maybe here, we need to blur the energy. In fact, the energy is also not a line, but it's blurred. The energy fluctuates, and this fluctuation makes fluctuation in the frequency, and then we have a line width. Now, what causes this blurriness? There are several reasons. One reason is simply the uncertainty principle, right? Because what is the uncertainty principle? Let's say this molecule in the excited state, it will not live there forever. The excited state is metastable, it will come down. It goes up, will come down radiatively or non-radiatively, and it has certain lifetime, tau, or you can call it the average time that the system is in the excited state. And the uncertainty principle will tell us that the product of the energy and the time is equal or maybe bigger than something. something related to Planck constant. This is the Heisenberg principle, which means the energy and the time width are inversely proportional. So what that is called lifetime broadening. Lifetime broadening means that the shorter the time is, the more blurrier the energy is, the wider is the transition. And usually in lifetime broadened bands, they have a shape that has this function in the very most generic form, is called Lorentzian function, right? It is kind of a bell-shaped curve. All right. Now, what I wanted to say was not exactly that. What I wanted to say was there is homogeneous and there is inhomogeneous broadening. Now let's define that. Homogeneous broadening, this term comes when we have not only one molecule, but we have an ensemble. When you have an ensemble, by definition, the homogeneous broadening is broadening effect that acts in the same way on all molecules in the ensemble. And for example, the lifetime broadening defined in this way, if we have all the molecules in our solution or gas, they have the same lifetime, they will be broadened by the same way, that is homogeneous. On the other hand, we can have inhomogeneous broadening when we have different molecules have different broadening in the ensemble. So the broadening effect acts differently on different molecules. So for example, we can have a solution. We are interested in the solid. So the solid is dissolved in the solvent, and let's say the solid can make hydrogen bonds or whatever interaction with the solvent, and some molecule maybe has a hydrogen bond and another does not have, then this can change the energy of the transition. That is inhomogeneous broadening. So it is kind of fundamentally different, but also not so different, because the hydrogen bond, let's say, is a dynamic thing. It can form and then it can break many times. So on average, maybe it's the same for all molecules. The difference is only about time scale. Basically, if we have slow enough broadening effects, they can be inhomogeneous. If they are too fast, then they become homogeneous. So the other thing that is important to remember is that when we have inhomogeneous broadening, we can illustrate it like this. We have one molecule here, and then we have some average displacement of energy or average energy difference. So we will have distribution of energies, random. And then if we write a distribution, a random distribution, you know, it has a different shape. If we just keep adding, we will eventually form what kind of shape? A Gaussian. Yeah. So the line shape in the inhomogeneous limit is Gaussian, in the homogeneous limit is Lorentzian, in the realistic limit is something in between, because we have one Lorentzian here, and then another here, and then another here, another here, then we make a distribution of those. It becomes a mixture of Gaussian and Lorentzian shapes. What is can be formulated as a Voigt profile, Voigt function, but let's not go too much in mathematics now. So it's just we know now what is homogeneous and inhomogeneous broadening. Now what else I would like to remind you is what is quantum coherence. Now we say the molecule can be in a ground state, or it can be in an excited state. Right? These are eigenstates, so they are solutions of the Schrödinger equation. But we know any combination of solutions of the Schrödinger equation is also a solution of the Schrödinger equation. So any mixture of eigenstates is also a valid, pure quantum state, right? Only we call these states coherent superposition states, right? And if we remember, so let's say we have a ground state, we have excited state, and we can make a coherent superposition of those, where the system is dead and alive, right? Or ground and excited at the same time. That is a quantum state. And we know about those states which are not eigenstates. What do we know about them? We know that in the eigenstates, anything that you measure is stationary in time, right? But in coherent superposition states, you can find observables, for example, energy, which are not stationary but fluctuate or oscillate. And they oscillate with this term because the coherent superposition here is the wave function is a linear combination of the ground and excited state. But these wave functions, they have two terms, right? They have a time independent and a time dependent term. The time dependent term in any eigenstate cancels out, but in this case it does not cancel out. And then we have time dependence, which is like that. Let's say the system is in the ground state, and then we can send it into a coherence between the ground and excited state. It will move constantly between those two with some frequency. And this frequency is what? This is called Rabi oscillation. This frequency is simply the energy gap between the ground and the excited state. Now, normally other than vacuum and on paper, this will not live forever, but it will slowly diminish over time, or very fast. This is called dephasing, loss of coherence. Very important. So, all those spectroscopies that we're talking about, including Panthrope and two-dimensional spectroscopy, are coherent spectroscopies. This is not what I was talking about. Yeah. What we are measuring is the system in a coherent state, and we know that in a coherent state, these oscillations, they cause electromagnetic radiation to be emitted from our signal, and that is what we detect. Okay. So also it's nice to know when we talk about coherence, it's very useful to use the density matrix. Density matrix is just is defined like this. You know, we have this is the wave function, right? In Dirac notation, it's called what is it called? This is a ket, and we have this is the complex conjugate of the same wave function. In Dirac notation, we call it a Bragg, and that product is kind of the probability of the system that is in that state. And this is, we call it density matrix. Yeah. Ready to finish. Okay. Density matrix. Right. Really doesn't want to come back. You cut that part from the YouTube, okay, Peter? All right. Now, the density matrix in the ground state looks like this. This is, let's say, our first state. And in the excited state looks like that. This is our second state. The diagonals basically give us the probability that the system is in this or that state. And in the superposition state, we have, let's say in this case, equal probability that the system is in either the ground or in the excited state. And then we have these off-diagonal elements, and these elements signify the coherence. Okay, this couples the two states. Okay, and this is actually the off-diagonal elements of the density matrix. They cause, if you derive the, okay, let's try again, very quickly. What is also very useful is to know that when we measure electromagnetic radiation from the sample, basically what we measure is polarization. And polarization is defined as the net dipole moment, or it is the expectation value of the dipole moment operator. And a useful thing about the density matrix is that any kind of operator can be, the expectation value of any operator can be found normally in a wave function. It is like this, right? Then you have the operator and then you do this integration. But with the density matrix, this is equal to, let's put it here, is equal to the trace of the operator, whatever operator, and the density matrix. Okay? The trace means just sum the diagonal elements, right? So for the dipole moment, bear with me, it becomes clear in a second. For the dipole moment, that is the trace. Basically, we multiply the dipole moment operator with the density matrix, sum all the diagonal elements, that is our polarization. And it turns out that if we do that, only the off-diagonal elements come into the trace of the density matrix. Okay. Simply because the dipole moment is also an off-diagonal operator. Okay. That's coherence for you. Now that we perfectly know what is coherence, we can move on. So, normally we don't have just one molecule. We are talking about complexes with many different kind of molecules, and they interact with each other, especially they interact with their transition dipole moments. So we have this Coulombic dipole-dipole interaction, which causes things like, for example, excitation energy transfer. What does that mean? Here we have two identical molecules with just one excited and one ground state. What can happen is because of the interaction of the dipoles, the transition dipoles, the excitation can jump from one molecule to the other molecule, and this is usually a very, very well-known effect, which is formulated theoretically by Förster, and we call it Förster resonance energy transfer. And we know many things about that. This is the rate of energy transfer according to the Förster mechanism. It depends on the distance between the molecules, on the inverse power of 6. Depends on the orientation of the transition dipole moments here in the kappa. And it also depends on this term. What is here is the fluorescence emission of the donor. Here is the absorption of spectrum of the acceptor, and the integral of this is the overlap integral of the two spectra. What does that? This is the resonance condition. Okay. Here, because these are identical molecules, of course they overlap because the energies are the same. But actually, what we have, it's, the first mechanism is what is called the inhomogeneous limit. We have ground state, excited state, and this one fluctuates, right? But it will equilibrate to some equilibrium position. And after that is equilibrated, the other state, if it has matching energy levels, that's the donor molecule, that's the acceptor molecule, after the equilibration there can be a transfer of the excitation without any loss of energy. That will be conservation of energy. And then this one can equilibrate down, maybe, if it has lower levels, then we lose part of the energy. So basically what happens is we have one equilibrated system, then the excitation hops to another, then it equilibrates again. When we say equilibration, what we really mean is that the system, that this is vibrational relaxation in another term. Okay? If we draw potential energy surface in the ground state and in the excited state, this is the position, the atomic nuclear coordinates, and then there will be some slide over that potential energy surface. That means the nuclear coordinate will rearrange to another equilibrium position. All right. So in the first term mechanism, what is important to remember, this is very fast and much faster than the transfer itself. That's all. Now, if that condition is not satisfied, then we have another situation. Then we cannot treat the two molecules as separate molecules anymore, and we have to calculate the excited states for the whole entire aggregate. And this is called the excitonic interaction. When the coupling is stronger, so that the energy levels of the new system are no longer eigenstates of the individual molecules, but they are mixed states. So what is here illustrated in this picture, if we have two molecules and they are strongly interacting, the Hamiltonian of the new system contains this interaction term, which is the Coulombic interaction, and it has this off-diagonal, this interaction term comes off-diagonal of the Hamiltonian. That means the Hamiltonian is no longer diagonal, which means that the energies are no longer eigenstates. We have new eigenstates, which we can obtain by diagonalizing this Hamiltonian, and then for the system, or just for a dimer, it turns out if the energies are identical, we have the new states are one above and one below. Simply one is plus and minus the interaction energy. And this is called the excitonic split, or the Davidov split. And it causes that in the absorption of this excitonic dimer, we see no longer one absorption band, but two. This is the excitonic split. And we can also calculate the wave functions with this approach. They are just linear combinations of the monomer wave functions. What that means is that both monomers, both molecules, contribute to both of the new excited states. In other words, that means the excited states are delocalized. All right? So we can no longer assign one state to one molecule and the other state to another molecule. What happens is that we have, when we excite one, we excite coherently superposition of two sites, of two molecules. And then the energy transfer in this case is not a hopping mechanism like in the first limit, but is what we call coherent transfer. All right, this is just an example of an excitonic molecule. In the monomer, we have absorption band, single absorption band, and in the dimer, it splits in two, and then we have the distance between those is just twice the interaction energy. All right, and then we have the weak coupling limit, where we have localized excited states, and then we have energy transfer as a hopping process, and we have the strong coupling limit, where the excited states are delocalized, and we have these wave-like excitation motions. Okay. Now, we can move on to try to see how we can actually study these processes, right? And I will remind the principle of the pump probe spectroscopy, which is like the classic. And so, if we want to study the dynamics, first of all, we need some maybe short laser pulses that can define sharp periods of time when we can start the kinetics of the system. We can excite the system or cause some change at what is called time, what we will refer to as time zero. And then, after a certain time, we can probe the system, right? This is the basics of the pump probe spectroscopy. We send a laser pulse that creates some non-equilibrium, some excited state, and then we wait a little time to see what will happen to the system after we probe it. And we measure the differential absorption of the probe pulse, which is with pump or without pump, right? This pump probe. Now, what I want to say here, which you may or you may not have talked about, is that pump probe is a third order nonlinear spectroscopy. That means we mix we have three interactions of the laser field with the sample, but we have only two pulses. So how come? It comes from what is called the phase matching condition, because in pump probe, the signal is emitted along with the probe wave vector. So then there is the law of conservation of momentum, says that the signal will be, the signal vector is the sum of all incoming radiation vectors, which means that it to be equal to the K1 is the pump, K2 is the probe, and then the signal is equal to K2, so it is K1 minus K1 plus K2. All right, this one cancels. What we have is three laser fields, or three interactions. 2 times the system interacts with the pump, and 1 time with the probe. Okay? And now, maybe I can explain that a bit. What does that mean? It's very convenient to express these processes in the density matrix formalism. Now what we said, the density matrix again, we have, let's say we have our 2-level system. One level is called the zeroth, the ground level, and one excited. So when the system is in the ground state, this is the density matrix. And when the system is in the excited state, the density matrix is like that. But the system can be in something intermediate like this, which is a coherent state. All right? The cat of one state got with the bra of the other state. So there is something called the Feynman diagram, single-sided or double-sided. The Feynman diagrams are just a way to draw the interactions of the laser field with our density matrix. And in time, we can order them in time. So we have a vertical line, which is our time. And let's say absorption, just normal absorption. In the beginning, the system is in the ground state. We just write the ket. The bra will be just the same way, symmetric. We have the system in the ground state, and then comes the laser field, and then it causes the system to move up. And then in this formalism, finally, the electromagnetic field is emitted. Because if we draw here the other part, the blue is out. Continue with the green. They dry out. Okay. So here we don't touch. We just touch on the side of the ket. That means that basically this is a diagrammatic illustration of the multiplication of the transition dipole moment with the density matrix. And this interaction means on the left side, and if we have the arrow on that side, then it's like that. So this will operate on the bra side, and this will operate on the other way. This is the ket side, this is the bra side. Doesn't matter. This is very convoluted and weird way to express linear absorption, but it comes handy when we start to mix many fields, and it's a very good way to track what is happening with the system. In this, so I will draw it again in a more simple terms. Now we have one pump interaction, and it will go like. Can you see? So the pump comes, the system goes on to the excited state on the ket side. This is on the left side. This is coherence. Then the second interaction with the field moves the other side of the density matrix. And then we have both sides, which means now the system is in the excited state. Before that, is not yet in the excited state. So we need two interactions. And then comes for example, then can come the probe. Pulse can come here. When the arrow is out from the diagram, it means we go back. We emit, go down in energy or in frequency, and then we are back in the coherence, and this coherence emits our nonlinear signal. So this is a pump probe signal, but this is actually what is called stimulated emission. There are many different combinations to do these arrows, and so there are different what is called responses. Like this is only one of them, what is stimulated emission, and it can